AC conditions, the importance of RMS values, power rating, practical limitations, and key points useful for examinations and interviews. In AC circuits, voltage and current vary continuously with time. Because of this variation, instantaneous values cannot be directly used to calculate heating effects. The heating effect in a resistor depends on the average value of the square of current. RMS value is used because it provides an equivalent DC value that produces the same heating effect as the AC current. Power dissipation in a resistor is proportional to the square of the current multiplied by resistance. RMS current produces the same amount of heat as a DC current of the same value. Peak values do not determine power loss because they occur only for a very short duration and do not contribute significantly to heating. RMS value is defined as the DC value that produces the same heating effect in a resistor as the given AC value. This definition is commonly asked in interviews and clearly explains the physical meaning of RMS. The power rating of a resistor indicates the maximum amount of heat that the resistor can safely dissipate without damage. Exceeding this rating can cause overheating, change in resistance value, or permanent failure of the resistor. In DC circuits, the power dissipated in a resistor is given by P equals I squared R, or V squared divided by R. This power is entirely converted into heat, and the resistor must be designed to withstand this heat. In AC circuits, power dissipation is calculated using RMS values. The power is equal to IRMS squared multiplied by resistance, or versus RMS multiplied by IRMS. Even though voltage and current vary with time, heating depends only on RMS values. Since heating depends on RMS current, both AC and DC currents of the same RMS value produce the same heating effect. Therefore, the power rating of a resistor is the same for both AC and DC applications. In practical resistors, certain limitations arise at high frequencies. Skin effect increases the effective resistance, parasitic inductance causes additional losses, and the overall power handling capability may reduce. These effects are not present in ideal resistors. Resistors are classified into different types such as carbon composition, carbon film, metal film, wire wound, and non-inductive wire wound resistors. Each type is selected based on cost, accuracy, noise level, power handling, and frequency of operation. Carbon composition resistors are inexpensive but have high noise and low stability. Carbon film resistors provide better stability, while metal film resistors offer high precision and low noise, making them suitable for accurate electronic applications. Wire wound resistors are used in high-power applications. They consist of a metal wire wound on a ceramic core. However, this coiled structure introduces parasitic inductance, which affects their performance in AC circuits. Because the wire is coiled, wire wound resistors behave like inductors at higher frequencies. As frequency increases, inductive reactance increases, limiting their use in high-frequency applications. Inductive reactance is given by XL equals 2 pi FL. This equation shows that inductive effects increase directly with frequency, which explains the frequency limitation of wire wound resistors. When resistance and inductive reactance are both present, the total impedance becomes the square root of R squared plus XL squared. As a result, the component no longer behaves as a purely resistive element at high frequencies. Non-inductive wire wound resistors are designed using special winding techniques that cancel inductance. These resistors are commonly used in AC power circuits, load banks, and testing applications. When an AC voltage is applied across a resistor, the instantaneous current follows Ohm's law at every moment. The current reverses direction along with voltage polarity, and no energy is stored. All electrical energy is dissipated as heat. In an ideal resistor, voltage and current are always in phase, resulting in a phase angle of 0 degrees. The impedance is purely resistive and does not depend on frequency in ideal conditions. In practical resistors, parasitic inductance becomes significant at high frequencies, skin effect increases resistance, temperature rise alters resistance value, and power handling is limited by the resistor's rating. For interview preparation, it is important to remember that a resistor behaves the same in AC and DC on an RMS basis, only the resistive component consumes real power, the power factor of a pure resistor is unity, and wire-wound resistors are frequency limited. In conclusion, RMS values determine heating and power loss in resistors. AC and DC power ratings are identical, practical resistors have frequency limitations, and correct resistor selection depends on both power rating and operating frequency.